This is the second part of Chapter 11, Section 1 for Business Calculus. And we're beginning with Example 3, picking up where Part 1 left off. And we are to determine the limit as x approaches 2 of h of x for a function h, which is defined by x squared if x is not equal to 2. Or if x is equal to 2, then the value of h of x is always going to be 1. And this is what we call a piecewise function. One of the things that I want you to understand how to do is, in order to graph this, one of the ways that you can graph this function is to enter into your calculator y1 is equal to, and since this is piecewise, it's actually going to be the sum of two pieces of the function. So we're going to have piece 1 and piece 2. The first piece, which the rule must be written in parentheses, is only useful and appropriate when x is not equal to 2. And you will find the not equal to sign on the second and math key. And then the second part of the function is just simply the number 1. And the rule there is when x is in fact equal to 1. And again, in order to find the equal to sign, that will be on the second and math menu. That's actually called the test menu. And it says that we want to determine the limit. Well, if x is actually 2, then h of 2 is equal to 1. But we are not really so much interested in this as we are what is happening when h approaches 2. Now, if it's approaching 2 from the left, then what it's going to do is use the rule for x squared. And we have already seen before how to build a table. And in fact, we have built the table for f of x is equal to x squared. So, in order to approach negative 2 from the left, we're going to start out with x is equal to, or excuse me, we're approaching 2, not negative 2. So we're going to start out with x is equal to, since we're going from the left. Then we're going to start out at 1 point. Start at x equals 1.9. And then we're going to let equal 1.99. And then we're going to let it equal 1.999. And see what happens to h of x as we do this. So 1.9 squared is 3.61. And then 1.99 squared is 3.9601. And 1.999 squared is 3.996. 001. So as h, if you're finding the limit of h of x, and letting x approach 2 from the negative side, then that limit appears to be, let's see, more than 3.5. 3.96 is close to 4. 3.996 is even closer to 4. So that limit appears to be 4. And then following the same logic, we will let x be numbers from the right of 2, starting with 2.1, 2.01, 2.001, and of course we could go further, but we just want to look at those few and see if we can notice a pattern. So when you take 2.1 and square it, you get 4.41. And when you take 2.01 and square it, you get 4.0401. And then when you take 2.001 and square that, you get 4.004. 001. So what we see is that as x approaches 2 from the positive side, for h of x, what's happening is we go from 2.1 to very, very close to 2. We get 4.4, then 4.04, and then 4.004. So again, we are approaching the same limit of 4, even though h of 2 itself is equal to 1. So what actually happens in this parabola is that if we drew a picture of it and focused on what's going on around 2, we would see something like this. Where this is the value 2 for x, and we would see that the h of x value that's being approached is 4, when in fact the value of the function itself at 2 is actually 1. So that's what the graph would look like. Now in this case, we're trying to let x approach negative 2. And what you need to notice here is that if x is equal to negative 2, then f of negative 2 is 3 times 2 plus 2 over 2 times, negative 2. 2 times negative 2 plus 4, which means that f of negative 2 is negative 6 plus 2 is negative 4, over 2 times negative 2 is negative 4 plus 4 is 0. So f of negative 2 is actually undefined. But we're not really interested in what happens at exactly negative 2. We want the limit as x approaches negative 2. So numbers a little bit to the left of negative 2 would be numbers like x equals negative 2.1, x equals negative 2.01, x equals negative 2.001. And then when we plug those numbers into the calculator, and I'm going to use the table to do this. Then we see that at negative 2.1 we have for f of x, we get 21.5. And when we square, or when we plug in negative 2.01, we get 201.5. And when we do negative 2.001, we get 2001.5. And if we go one step further to 2.0001, we get 20,002. And actually, the exact value of that is 20,001.5. If I actually take the unrounded answer. But you can see what's happening is as x approaches negative 2 from the left side, the number increases very, very quickly. And what we say is that this is increasing without bound, or that the limit as x approaches negative 2 from the negative side is going to be infinity. Now, if we approach from the right side, from the positive side, then we're going to let x equal negative 0.9. And then negative 0.99. And then negative 0.999. And if needed, we could go further, but I think we'll probably go with just those three x values because we should see a pattern. And of course, we're still looking at f of x values. So again, making the table, I'm going to go negative 0.9, negative 0.99, negative 0.999. And what I see that is, I'm sorry, I've totally messed up. This should not have been negative 0 point. Let me back up here just a second. Those zeros should have been ones. because we're trying to get close to 2, not 1. So negative 1.9, negative 1.99, negative 1.999. And what we see happening here is that we begin with f of negative 1.9 is negative 18.5. But f of negative 1.99 is negative 198.5. And negative 1.999 is negative 1998.5. So if you notice here, what's happening is we're getting more and more 9s in there, which means that number, once again, the limit as x approaches negative 2, but from the right, is also infinity, but because of this negative sign, then the value for approach from the right is negative infinity. And graphically, if we look at this function, now this is the table that I've been building for that function. And this is just a bigger version of the table. This is the window that I'm looking at the function on, so I think you'll find that pretty interesting, because the window I'm choosing is the decimal window times 2. To get there, what I did was I used the zoom button, and I did zoom 4, which is your decimal window. And then on that window, I multiplied everything times 2. So it actually originally said negative 4.7 for x min, and I multiplied that by 2 and got negative 9.4, and then positive 4.7 gave me positive 9.4, and then on the y's I multiplied instead by 3. So negative 3.1 times 3 gave me negative 9.3, and 3.1 times 3 gave me 9.3. So what that gave me was a window that was approximately the same as the standard window, which goes negative 10 to 10 in both directions. But I wanted to actually be able to see the discontinuity. And when I do this, you will see that we do, in fact, have a discontinuity, which we knew about because x is not allowed to be negative 2. So what actually happens as you approach from the left, you see that you are approaching positive infinity. And as you approach from the right, you are approaching negative infinity. So the graph shows you this, as well as the previous tables and numerical values that we were looking at. So again, we see that the limit as x approaches negative 2 from the left is positive infinity from here, and as x approaches negative 2 from the right, which is this direction, we see that it approaches negative infinity. So what we want to talk about here is the language that we're going to use with this. And since the limit as x approaches 2 from the left increases without bound, that's the other language that we use, is that it increases without bound, then the short way to say that that happens is by using this limit notation. And as you approach negative 2 from the right, we say that it decreases without bound. It goes lower and lower and lower. And the way that we say that with minimum symbolics is to say the limit as x approaches negative 2 from the right of f of x is negative infinity. Notice, however, that the limit as x approaches negative 2 of f of x itself does not exist because it violates one of the rules. And one of the rules is that the limit doesn't exist if the right-hand limit is not the same as or does not equal the left-hand limit. And certainly infinity is not equal to negative infinity. So the limit doesn't exist. So in answering this question, then, the shorthand way that we'll often do that is we'll say it does not exist, or just simply D-N-E for does not exist. Here we have another function that is a rational function. This function's not defined at x equals 0 because what we would have at x equals 0 would have been the absolute value of 0, which is 0, divided by 0, and except for 0, we usually think, well, anything over itself is 1. Well, 0 over 0 is an indeterminate form, and we'll just let it go that that is not defined or undefined. So the fact that we're taking the absolute 0, we're still not able to divide by 0. That's what you want to keep in mind. However, when x is a positive number, the absolute value of x is equal to just x. And so if x is a positive number, the absolute value of x over x is going to be positive 1. And this is shown on this part of the graph. So this is at the value positive 1. However, when x is less than 0, the absolute value of a negative number is equal to the opposite of whatever x is. Now that sounds a little confusing, but if x is negative 1, for example, if we take the absolute value of negative 1 and divide it by negative 1, this is what's going to happen. The absolute value of negative 1 is positive 1, but you're still dividing by the negative 1. Or if it were 2, it would be positive 2, but you're still going to divide by negative 2. And in every case, that's going to be equal to negative 1. And that's what's being shown on this side of the graph, is that everything that's negative, the absolute value of x over x is going to be a negative 1. But that just tells us that the limit as x approaches 0 from the negative side of that function is equal to negative 1. And the limit as x approaches 0 from the positive side is going to be equal to positive 1. And since negative 1 does not equal positive 1, then the limit does not exist. So this just summarizes what it takes for a limit to exist. Basically, it says that if f of x becomes infinitely large in magnitude, positive or negative, as x approaches a number from either side, then we say that the limit is either positive infinity or it's negative infinity. And in either case, that limit doesn't exist because, for one thing, infinity is not a number. But on the other hand, usually when this happens, it's because one of the limits does approach positive infinity and the other one approaches negative infinity. So they don't match is what the real problem is. Now, if x becomes infinitely large in magnitude and positive as x approaches from one side, and increasingly large in magnitude or negative as x approaches from the other side, then that limit does not exist. So what this is saying here matches up with this picture. What this is saying on the first one says that even if you approach positive infinity from both sides, that limit still doesn't exist. And that's because you're not going to ever come together up here anywhere. Infinity is not a place. Excuse me, it's not a number. It's simply a place. It's an increasingly large number, so it's just an idea. And then finally, the limit doesn't exist if the left-hand limit does not equal the right-hand limit. So if the left-hand limit is L and the right-hand limit is M, then L isn't going to equal M. And that means your limit doesn't exist. In other words, this is what happened with our absolute value function, where if you approach from the negative, we had this. If you approach from the positive, we had this. But in between there, we're not approaching the same thing. So this will kind of summarize our explanation of what goes on with limits. And the first thing that we're going to look at, and I'm going to try to reposition this a little bit so that you can see it a little better. Here's x equals -6. If we approach -6 from the left, we're going to infinity. If we approach it from the right, then it's negative infinity. And for that reason, the limit as x approaches -6 does not exist. Now at this point, if we're trying to approach the number 4, when we approach from the left, the approach is for 2. But if we approach from the right, the result is 3. And since 2 doesn't equal 3, the limit as x approaches -4 does not exist. Now, the limit of f of x as x approaches 0 is actually 3.4, even though f of 3.4 or f of 0 is undefined. F of 0 actually, well, no, I said it's not defined. Actually, it is defined. It's defined as 2. So the reason this limit actually exists, even though it's not equal to f of 0, is because the left-hand limit comes to the same value as the right-hand limit. And they both approach approximately 3.4. Now looking at the next odd place, this is at x equals 3. And the limit as you approach 3 from the negative side goes to negative infinity. And if you approach from the right side, you still go to negative infinity. But although those are the same, the limit doesn't exist because infinity is not a number. It's just a place on the number line that we will never find. It's a concept. Then the next thing that we'll look at is what's happening here at x equals 4, because we notice there's a hole in the function there at x equals 4. So that means f of 4 is undefined. But if you approach 4 from the left and you approach 4 from the right, those are equal. Therefore, the limit does exist, and it appears to be 1, even though f of 4 is not defined. So if you can analyze a graph like this and tell me why the function the limit exists or doesn't exist at any particular point, then you have a good understanding of what a limit is. Now the last part of this, we're going to look at something called rules for limits. And other than leaving this slide in here and telling you that this is the rules for limits, what we're going to do is we're going to look at some examples. And I'm not interested in you actually memorizing the rules. I want you to get the idea. Basically, if k is a constant, then the limit as x approaches any value is still going to be k, because there's no x in that function. It's just a horizontal line through whatever number k is. And if you have k times a function, basically you take the limit of that function as x approaches a, and then you multiply it times the limit as x approaches a with k. So if you have a multiplier of a function, you can factor out a common factor that's a constant. Then you just hold that constant out to the side and take the limit of the function without that multiplier. This is easier to understand actually in plain English. If you've got a function f of x and g of x, and you need to find the limit of their sum or their difference, then you find the individual limits and either add or subtract them as is indicated by the sign. So what this says is the limit of the sum of f of x and g of x is the sum of the limit of f of x plus the limit of g of x. And the same thing with subtraction. If you have the limit as x approaches a of f of x minus g of x, then the actual answer is going to be take the limit of f of x, take the limit of g of x, and subtract them. The same thing applies to a product. If you have the limit of a product of two functions, then take the limit of each function and multiply those two limits together. And if you have the limit of a quotient of two functions, then take each function's limit and divide those two limits, as long as the limit of the bottom function is not 0. So this might be useful. We're going to look at a couple of polynomials here. So if a polynomial, this is a few more rules. If p of x is a polynomial and we're taking the limit as x approaches a, as long as it's a polynomial, then we can actually just plug in whatever the number is and find the limit. And the reason for that is because it's continuous for all values for the polynomial. So like it was with x squared, you could actually just plug in and square the number to find out what the limit was as you approach that number. This one talks about powers. It says that if you've got a power on a function and you want to find the limit of that function raised to a power, basically just find the limit of the function and then raise it to that same power. And this says that if the limit of f of x as x approaches a is equal to the limit of g of x as x approaches a, that means basically those functions must have been equal to each other. And for any number b greater than 0, This says the limit as x approaches a of any number b, which is the base of an exponential function, is going to be, take the limit of that base. I'm sorry, not the base. Take the limit of the power, which is what it's doing here, and then apply the limit of the power to that same base. And then this is what you would do if you had log functions. And we're not going to worry a whole lot about those last few rules. Let's see if we can do a few examples, though, to apply some of these. So, suppose we have the limit as x approaches 2 of the function f is equal to 3. And the limit as x approaches 2 for some other function, g of x, is equal to 4. And what we want to find is the limit as x approaches 2 of the sum of those two functions squared. Well, the way the rules work is you can take the limit of the first one and the limit of the second one, and because these are being added together, you add their limits. And then because that sum is being raised to the second power, then you're going to raise that second power on the sum of those two functions. Now the limit of f of x as x approaches 2 was 3. And the limit of g of x as x approaches 2 was 4. And 3 plus 4 is 7. And then because this limit is squared out here, 3 plus 4 quantity squared is 7 squared, so that limit is 49. Now, even though this is a quotient, we can't use the quotient rule because we're trying to take x approaches negative 3, when in fact if x actually is equal to negative 3 plus 3 will give us a 0 in the denominator. And that's a problem because we don't want this to be undefined. And actually, if you plug in negative 3 in the numerator, what you see happen is that that's also 0. So not only is it undefined in the denominator, 0 over 0 is meaningless because you can't divide 0 by 0. It's the only value, the only constant that cannot be divided by itself and come out to be 1. So what you can do, though, is you can simplify the function by rewriting it. So what we're going to do to rewrite the function is we're going to take x squared minus x minus 12 and rewrite it as x plus 4, x minus 4 and x plus 3. And then we're going to have that over x plus 3, and what's going to happen then is the x plus 3 is going to cancel. So this function that we started out with is equivalent to just the function x minus 4 as long as x does not equal negative 3, because there was still this original restriction that x couldn't be negative 3. But since we're taking a limit as x approaches negative 3, it's not actually equal to negative 3, then what actually happens then is x minus 4, if x is negative 3, is negative 7. So we're not letting it equal negative 3. We're plugging in negative 3 into this. and then we rewrite the fraction. So here we have another example. Find the limit as x approaches 3 of a trinomial divided by a square root function. Now the only issue we would have here would be if x were -1, then we would be taking the square root of 0, which is 0. So that means x can't be -1. We also have the issue that if x plus 1 is less than 0, in other words, if it's negative, then there's going to be a problem. So x cannot be less than 0. I'm sorry, not less than 0, less than 1. So if x is less than 1, let me just put it this way. If x is less than 1, that means you're taking the square root of a negative number, and that's not allowed. So the only restriction we have here is that this function is fine for all x greater than 1. We have to use x larger than 1. That function doesn't even exist for x less than 1, or even x is equal to 1. But fortunately, we're taking a limit for x is greater than 3, and that's certainly greater than 1, so we're going to be okay. So what we're going to do then is we're first going to take the limit as x approaches 3 of x squared minus x minus 1. And then we're going to divide that by the limit as x approaches 3 of the square root of x plus 1. Now, since this is a polynomial function, then we can take the limit as x approaches 3 by simply saying 3 squared minus 3 minus 1. And since this is a radical function and 3 is in the domain of the radicand, then we can simply take the square root of 3 plus 1 to get that limit. So 3 squared is 9 minus 3 is 6 minus 1 is 5 over the square root of 3 plus 1 is 4, which is 2. So the limit as x approaches 3 of the original function is 5 over 2. Now this spells out the rules that we were able to use, but it's exactly the same process that we just went through. So here we have an example of a word problem that's an application of limits. It says, suppose that we have a small pond that normally contains 12 units of dissolved oxygen in a fixed volume of water. And at the time t equals 0, what's happened is that they've introduced some kind of organic waste into that pond. Organic waste might be any of a number of different things, but maybe they cleaned out the barn and they dumped all of the waste out of the barn into the pond, which is not a bright thing to do because then you're going to poison all your cows. But they've done this for whatever reason. It could also be possible that the organic waste is a byproduct of some kind of manufacturing process. But they've dumped this waste into the pond. Now, that organic waste is going to be broken down by oxygen. Well, what happens as the oxygen breaks it down, the oxygen gets used up in the water, and it has to regenerate itself. So as the oxygen breaks down the waste, the oxygen concentration in the water is going to change over time. And T is measured here in weeks. So our function, f of t, says T weeks after they dumped in the waste into that water, this will give us the concentration of oxygen that remains in that pond. So the question is, what will be the ultimate concentration as T increases? What will be the ultimate concentration of the oxygen in that pond? Will it ever return to 12 units? Well, what you want to do here is you're wanting to let f of t, you're going to let t increase without bound. In other words, you're going to let it approach. Now, there's two ways to do this. One of the first ways you can do this is you can actually draw a graph of f of t. And a graph of f of t looks like this graph. And notice what happens is that at about 4 weeks, the concentration of oxygen has increased back up to somewhere between 8 and 9 parts per million. But before that, it had dropped, at the end of 2 weeks, it had dropped all the way down to 6. And within the first week, as a matter of fact, it dropped down to somewhere between 4 and 5. But it bottomed out and it turned around and started increasing again after that. So we see that it's increasing, but we also notice that it seems to be leveling out. Now, this is its original concentration. So what we notice is after about 12 weeks, it's back up around, but not quite equal to, 11. And then it keeps on increasing after that, obviously, but the question is it ever going to increase enough to get back to 12? Well, in order to investigate that, the best way to do it is to do this numerically. So again, remember that you can build your table. You simply go to y equals and enter the function. And then you make sure your table lets you ask for the independent variable. And then you go to second graph. And this is what you enter into your x values, because of course we don't have a t variable on our calculator. So we enter in 10, and we see that at the end of 10 weeks, the concentration is 10.515. So then we increase that by a factor of 10 to 100, and we see that its oxygen concentration has increased to 11.85 after 100 weeks. So then after 1,000 weeks, and just for kind of getting an idea how much that actually is, this is a little less than 3 years, because there's, well, no, I take that back. Let's see, there's 52 weeks in a year, so this would be about 20 years. In about 20 years, it's back to 11.98. But that took 20 years, folks. And then after 10,000 weeks, it's at 11.9985. And after 100,000 weeks, it's at 11.99985. So it's approaching to the number 12. But it's never going to get there. It doesn't matter how many zeros we string on over here, it's never going to get there. And you can prove that to yourself by using your calculator. So here's one of our final concepts here, is how do you take limits at infinity? Basically, there's a rule about taking limits at x as x approaches infinity. If you've got a rational function, and this is a rational function, where x is in the denominator, and x has been raised to a power, what's going to happen is as you raise this number to a power, think about what happens as you, just a small number like 2. 2 to the first power, oh, phooey. Well, I think we're just going to have to live with it. So let's say we take a number like 2. 2 to the first power is equal to 2. 2 to the second power, 4. 2 to the third power, 8. 2 to the fourth power, 16. 2 to the fifth power, 32. 2 to the sixth power, 64. 2 to the seventh power, 132. 2 to the eighth power, 264. 2 to the ninth power, 528. And it's just going to go on from there. So notice that it starts out small, but it grows pretty quickly as that power gets bigger. Now imagine that you're taking these numbers, and this is going 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/132, and onward. What's happening to these fractions as just a small base like 2 increases in its power? Well, it gets smaller and smaller and smaller and smaller and a whole lot smaller and much, much smaller. And as we get to 1/528, that's a really small number. And the next one's going to be 1/1056. So this is going to continue. What's happening to these numbers as x approaches infinity, one over x to a power is going to get very close to 0. And actually the same thing is going to happen. If these were negative, it wouldn't make any difference, because when you square or cube -2, what's going to happen is they're going to alternate. This is going to be this is going to be 2. This is going to be -2. This is going to be 4. This will be -8. This will be 16. This will be -32. Then 64. Then -132. Then +264. Then -528. But still, what happens is the only thing that's going to change is these fractions. The first one's negative. Next one's positive. Next 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 one's negative. But this is getting close to 0, and this is getting close to 0. It doesn't matter if it's positive or negative. What's happening is the amount of the fraction actually gets very small. And small from the negative direction can still approach 0. So even if you're approaching from the negative side, you're still going to get 0. So keep that in mind for something called limits at infinity. As x increases without bound, if you've got x to a power in the denominator, the limit's going to be 0. Now, we're going to use that same idea to talk about this problem. If you have the limit of something like 8x plus 6 over 3x minus 1, and your x is approaching infinity, this is a method that you can use to be able to figure out what your answer is going to be. What you want to do is you want to divide by the highest power of x, and it's important that it be the highest power of x in the denominator. So if we look at this function, the highest power of x in the denominator is just x. So what we're going to do is we're going to take that x and divide it into 8x, as we did here, and divide it into 6, as we did here, and divide it into 3x, as we did here, and divide it into negative 1, as we did here. And then we're going to try to simplify that. Remember, we're taking the limit as x approaches infinity. So now 8x over x comes out to be 8. And 3x over x, because these x's cancel in these first two parts, then that just becomes 3. And then 6 over x is the same as 6 times 1 over x. Now, if you let x increase without bound, the limit of 8 as x approaches infinity is just 8. Because 8 doesn't care what x does. It doesn't have any x's. And if you let x approach infinity for 3, the same thing happens. Because 3 says, well, I don't care what x does. I don't have any x's. I'm going to be 3. But by the rule we just looked at, the quantity 1 over x, as x approaches infinity, it approaches 0. And 6 times 0 is 0. Same thing with 1 over x in the denominator. As x increases without bound, 1 over x approaches 0. And so 8 plus 0 is 8, and 3 minus 0 is 3, and that is the limit of this function, 8/3. Now this is just a little warning. You do need to actually do this process. Don't just automatically assume because this one came out to be 8 over 3 that all you're going to have to do is just take those first two numbers in your numerator and denominator. It won't work that way. You have to actually do this process, and then remember that the limit of 1 over x, or 1 over x to any power, is going to be 0. So let's So here again, we have 3x plus 2 over 4x cubed minus 1, which is a rational function. And we're not worried about where the denominator is going to be undefined because we're letting x increase without bound. So we're just going to let x get really big. And again, we're going to divide by the highest power of x in the denominator. And the highest power of x in the denominator is x cubed. So when I take, and rather than go straight to all of this down here, I'm going to take 3x, and I'm going to divide it by x cubed. And then I'm going to take 2, and I'm going to divide it by x cubed. Then I'm going to take 4x cubed, and I'm going to divide it by x cubed. And then I'm going to take the 1 and divide it by x cubed. Now, this is what's going to happen. The x in the numerator is going to take away one of the x's in the denominator and leave us with x squared, which is what happens here. Rather than keep this 2 over x cubed, I'm going to pull the 2 down in front, so it'll be a multiplier, and change that to 1 over x cubed, which is what they did here. And then in the denominator, 4x cubed over x cubed leaves me with just 4. And then 1 over x cubed is just going to have to stay like it is. There's nothing I can do with that. So here's what we're going to look at. Remember, the limit as x approaches infinity of 1 over x to any power, 1, 2, 3, whatever, is equal to 0. Whatever the power is, that limit's equal to 0, which tells me that this is 0, and this is 0, and this is 0, and 3 times 0 is 0, and 2 times 0 is 0. 4 remains 4, 0 remains 0. 0 plus 0 is 0. 4 minus 0 is 4, and if you have nothing and divide it up among 4 friends, all of them get some of the nothing, and they all have nothing, which is 0. So this limit is equal to 0. This is a good trick to know how to do, and it always works. So here's one more example. And notice again, the limit as x approaches infinity. The highest power in the denominator this time is x. So what we're going to do is we're going to take this function and we're going to transform it by dividing 3x squared by x, and we'll get 3x. And then we're going to divide 2 by x and get 2 over x. And then we're going to divide 4x by x and get just 4. And then we're going to divide 3 by x and get 3 over x. Now notice here that the denominator is going to approach 4 as x increases without bound, because this is 3 times 1 over x, and the limit for 1 over x is going to be 0, which is 0. So this is 4 minus 0, which is where you get just the 4. In the numerator, 2 times 1 over x is going to be the same as 2 times 0, which is going to again be 0. So actually, that's going to go away too. So these two things just kind of drop out and they don't matter. So the denominator approaches 4, but the numerator approaches infinity, because as you let x get bigger and bigger and bigger, then 3 times x gets bigger 3 times as fast. And with it growing that fast, dividing it by that lonesome little number of 4 makes no difference. So actually what happens is that as x approaches infinity, 3x approaches infinity. And infinity divided by 4 is still infinity. So this limit is actually infinity. The value of that fraction increases without bound as x gets larger and larger and larger. So now you've seen 3 different ways that you can use that rule about 1 over x, but you always do the same thing. You divide by the highest power of x in the denominator. Remember, it has to be the one in the denominator. So our last slide, and this is the end of our lesson, simply explains or summarizes the process for finding limits at infinity. Basically, it says that if you have some function that is the quotient of two other functions, and those two functions are themselves polynomials, as long as q of x is never equal to 0, that's very important, q of x can't be 0, then you can take the limit as x approaches infinity or negative infinity of that function by dividing p of x and q of x by the highest power of x in the denominator. That's the important. It has to be in the denominator. And then the rule for limits says that as x approaches infinity, for 1 over x raised to any power is equal to 0. Doesn't matter if it's positive infinity or negative infinity. So this is going to be the place where you're going to have to be pretty good at using your algebra, and that's why you had a skills check quiz to make sure that your algebra skills were up to par. So this concludes our lesson for section 11.1. I will have, I already have actually a lecture for 11.2 posted in Shobi, and I will be adding another lecture in Shobi to make sure that I've covered all the points that you need to hear about. Please let me know if you have questions.